So we can use these two things right here to kind of find values of L. So let's actually go to coding, because I've been doing math for an hour and I haven't actually written a line of code. Math that might not even be right. So let me move this little Twitch window. So let's go to our number theoretic transform. Am I in here? Okay. NTT.list. Oops. So we want to find some bounds. Let's just go to the bottom of the file. We can recreate this. So over, let me go back here. Where is my mouse? Let's choose this light blue. So we can actually generalize. Here I talked about for 1 billion digits, but this whole computation right here is we're basically changing the exponent here. So if we have 1 billion digits, we just need whatever the log 10 exponent is. So that would be, if we want a total of k digits, then we have the common log of k times log 10 plus log squared 10. So we're going to parameterize our stuff by doing this. 2 to the 33 digits. Then what you would have there is that'd be log 10 of 2 to the 33, which is 33 log 10 2 times the log 10 and so on. We'll see. Well, let's write the calculation for that out. So let's do this. Defun bounds or something like that. So num digits. So, well, what we're going to find out is if it'll overflow. The whole point of this computation is to look at what the bounds of overflowing are, if that makes sense. So we'll see what possible, and this totally constrains our length of our transform and the base integer sizes that we can use. So that's actually that's kind of the point of this program, is whether we'll get overflow or not. So let's call this thing over here, let's call this whole quantity, let's call that, I don't know, x or something. I don't know. It doesn't matter. Let x be this wacky computation, which is going to be the it's going to be a sum of 2 multiplications. This is defun log x log x2 defun log 10 x is log x10. Let's define these two little functions. So this first one is going to be log 10 of our num digits times our binary log of 10, and that's summed together with the binary log of the binary log of 10. So that's our x value. So so when we loop through b, well, again, we have this bound right here that b must be between 2 and 64. So let's do that. Loop for b from 2 to 64. When our inequality is satisfied, namely we have less than or equal to our top part of our inequality, which is minus x log b, And that's less than or equal to 65 minus 2b. I should say for lower equals this, and for upper equals this. When less than lower upper, do format D, base equals our base B, base width actually equals B, our transform length, or our log length is going to be 2 here. It's going to be ceiling of our lower and our floor of our upper. Let's see what happens here. So control 2. If I look at bounds of 1 billion, then we get this. We can have a, I'm going to make this easier, base width. Let's see, base equals some number here, D, which equals 2 to the power of D. I'm going to make this output easier to read. Okay, so if our base is 4, for example, and we need to represent 1 billion digits, then our length is going to need to be between 31 and 61. If our length is, so it basically says, so to answer your question, King Frederick 6, can you have 2 to the power of 33 digits? Let's look. 2 to the 33. So it's saying these are the parameters in which you can have such a thing. The most efficient parameter to have something that has 2 to the 33 digits would be this right here. We would need a base of 131,000, which is 2 to the 17, and we'd need an array whose size is 2 to the 31, which is EXP2 to 31 format TR, which is 2 billion, which I should have known because 2 to the 32 is 4 billion. The question is all this math correct? Let's do NP word width, which is 64. 1 plus the word width. Let's look at what we'd have on a 32-bit platform. Word width 32. Yeah, we wouldn't even be able to represent numbers with 2 to 33 digits on a 32-bit platform. That's precisely what this is saying. One other question is, do we do it with 60? Yeah, okay. So it looks like numbers whose base are relatively small are the most efficient, so to speak. This is kind of unfortunate. We have integers that we can natively represent as 64 bits, but what this is saying is that we can't use all 64 bits to represent our incoming number because we'll get an overflow otherwise. yeah, it's just, it's unfortunate. Let me take this. Sure. Okay. So, what do we need to do with this? Well, one sort of to do is to actually check the math here. Ensure that this math is correct. There are a few times where I kind of used a few weasel words, not weasel words, but I kind of weaseled my way out of a few hard things, such as, is it transform length times the modulus squared? Is it transform length times the base squared? Is it, you know, what is it? I was presuming that it's n times b minus 1 squared, you know. That analysis will need to be done in a more formal way and not kind of off the top of my head in Twitch chat. So we do get useful things. We want to now extract the maximum bound that we can choose. Let's see. So let's write this function. How should we do this? Let's say find appropriate base. I'm going to keep this bounds function actually, and I'm going to write another version of it, copy pasting, called find appropriate base. Find appropriate base and length. Find an appropriate number base and transform length to do multiplications to do and okay, so we'll probably want to go from 64 down to 2, so we want to start maximally and find something with lower and upper. So we want to find the maximum we want to find the maximum base with the minimum transform length. So the maximum base is going to be whatever b we find. The minimum transform length is going to be the ceiling of lower. So when lower is greater than upper, then what we want to do is return our values. We want to return our base, and we want to return the ceiling of our lower. So if we do this now, we do, let's see, find appropriate base and length. This tells us that our base is 15 and our transform length has to be 2 to the 31 elements long. Okay, this is good progress. So now that we have find appropriate base and length, now we need to find an appropriate modulus for that base and length. So for our number theoretic transform, we're computing everything mod m. Our requirement to do the multiplications is the I was just thinking of something else. I think I neglected one thing here, which is when you multiply two numbers of length L, your result is going to be of length 2L. We get a doubling here, and I don't think I represent it in here appropriately. So if we have 2 billion digit long things, I think what that means is that our